Hello everybody, and welcome to part B of exercise 4. This is the top of page 150 in the workbook, and we are continuing with the problem that deals with the electrical field where we have a point charge at the origin. Okay, and part B is asking us to calculate one of the integrals of the electric field over one of the surfaces that we described in part A. Let's remind ourselves what that surface was again. Okay, so they told us in part A that S1 was an arbitrary surface that kind of encloses the origin. So in our picture over here, S1 we were picturing as kind of the surface of just a blob of clay or something that's centered at the origin. We'd like to integrate and find the flux of the electric field through that surface. Okay, well, just so we don't have to keep flipping back and forth, I'm going to remind you here what the formula for the electric field was, just at the top of the page here. We made one slight alteration to that formula. We changed the epsilon to a K. Here's what the rest of the formula looked like. Okay, and they want us to calculate this integral. But that would be a really difficult integral to do because we saw on the previous page that S1 is an arbitrary surface. It could be really lumpy and not be regular at all. But what we showed in part A can be very helpful for us, and that is that integrating over S1 or S2 are going to give us the same value. And S2, remember, was a nice regular sphere that was centered at the origin. That's going to be a much easier integral than the integral over S1 would be. So we're going to start by just noting that we can do that. We can just replace the harder integral with the easier one. That was the whole point of doing part A, was so that we could do that. Okay, and then we'll remind ourselves of a formula for the dot product. We can break it down into, or actually this is not the dot product yet, just a general formula for the flux integral. We can break it down into those components, E dot n, where n just represented a unit normal vector. This was a technique that you used back in chapter 19 a couple of times. Okay, and now we're ready to think about that geometric way of viewing the dot product. E dot n breaks down into the length of E times the length of n times the cosine of the angle in between. Okay, but question for you. Okay, we're integrating over S2, which was the perfect sphere. What is the angle between our electric field vectors and a normal vector to S2? Let's go back to our picture again. Okay, so S2 was a nice regular sphere, the one that I'm tracing out here, and we made the comment at the beginning of our problem that our electric field has radial symmetry. It points directly away from the origin. Okay, and so that means then that these vectors are parallel. These normal vectors that we drew on S2 are parallel to the direction of our electric field. Okay, and since we gave S2 an outward orientation, okay, kind of the opposite of what was shown on the picture there, we know that this angle between the electric field vectors and our normal vectors is 0. Okay, which is really nice because cosine of 0 is 1, and that's true for every pair of E and M. Okay, so this simplifies then down to and then remember, we made the observation up above that n is just a unit vector, so what's the length of n going to be then? That's just going to be 1. So this simplifies even further then. Down to that. Okay, now let's remind ourselves what the formula for E was. That's sitting up here. So if we substitute that into this expression that we have, we are going to get the length of, okay, big expression here, And notice that there's some constants that we can pull outside. So if we take the length of this vector, let's see, can we pull anything out of that? Yeah, everything that we see there is a scalar, so we could pull that outside. Let's go ahead and do that and just see where this leads us. So we're going to get a kq over the length of r cubed. That's what happens after we take that outside of this norm here. And what's left over is just the length of r. Do you notice anything that cancels there? Okay, those cancel and leave a length of r squared down in the bottom. Okay, so simplifying a little bit more, k and q are both constants that we can pull outside of the integral, and what's left in the integral is kind of interesting. 1 over the length of r squared dA. But r is just a displacement vector that takes us from the origin to our surface, and remember that S2 is a perfect sphere of radius a, which means that the length of r equals a on the surface S2. Okay, that's just the radius of our sphere. Okay, so we can go a step farther and rewrite this as kq times 1 over a squared dA. Okay, and we're getting close. So I see another constant that we can pull out here now, this a squared. So let's pull that out. And what's left then is just the integral of dA over S2. Think about what we're really adding up when we do that integral. We're just adding up patches of area all the way over our entire surface S2. And we know that S2 is a perfect sphere. So that integral that I just underlined there, that's just the surface area of the sphere S2. And there's a formula for the surface area of a sphere. It just looks like 4 pi times the radius squared. So we're going to get kq over a squared times the surface area of the sphere, which looks like that. And we are almost done. One more cancellation. And what we wind up with for an answer is 4 pi kq. And what we have just demonstrated, okay, first of all, that's the flux of our vector field through this irregular surface that we started with. That result is a special case of what's known as Gauss's law in physics.